So here we have question number 4. It says X is CH3CH OH CH2CH3. That is butane 2-ol. Okay, that is butane 2-ol. The reaction between X and alkaline aqueous iodine produces a yellow precipitate. Okay. Give the name of the compound formed as a yellow precipitate in this reaction. So if you guys remember, this reaction is called the iodoform reaction, right? When you have a CH3CHOH group present, okay, you have a CH3CHOH group present like this, okay, then what you have over here is that the CH3 group breaks off, okay, with alkaline aqueous iodine, okay, alkaline aqueous iodine, okay, so over here we're using iodine and alkaline aqueous conditions. The CH3 breaks off and you end up making a salt of the acid. You end up making the salt of the acid, and the yellow precipitate that we produce is triiodomethane. The yellow precipitate that we produce is triiodomethane. So you either need to have a CH3CHOH group present, or you can also have a CH3C double bond O group. Okay, it has to be either an alcohol, okay, that has a CH3CHOH, or it has to be an aldehyde or a ketone that has a CH3C double bond O, right? So in either case, what happens is that first this guy is converted to this, and then at the end the CH3 breaks off to form CHI3, and you also form a salt of the carboxylic acid that has one carbon atom fewer. Okay, so the name of the compound that gives the yellow precipitate here is triiodomethane. Okay, that's this compound here, triiodomethane. What's the name of X? As we just mentioned, X is butane 2-ol. Again, this reaction is a test for either this group, CH3CHOH, this group, or it's a test for the CH3CO group. Okay, in this particular case, we had the CH3CHOH group. There are 3 structural isomers of X that are alcohols. Draw the structure of these 3 isomers of X. Okay, so here we have butane 2-ol. Okay, now in a straight chain compound, right? One possibility they've already given us butane 2-ol, which is this guy, right? This was given in the question. Now in a straight chain, are there any other possibilities for the position of the OH group? If I just had a straight chain, we're going to look at it chain by chain. So first, let's just look at straight chains. Is there any other possibilities for a straight chain isomer? You can have it on the second position, or you can have it on the first position, right? So you can have this also, right? This would be butane 1-ol. These are the 2 possibilities that you have for a straight chain. Okay, now that we've looked at the straight chain possibilities. Now let's look at the branching possibilities. Now if I had a branched chain like this, where this is the only branching that's possible, how many different places could the alcohol be in? How many different places could the alcohol be in over here in a branched chain? It could be on carbon number 1, right? It could be on carbon number 1 here, here, or here, right? Or it could be on the middle carbon. So one possibility that you have is the OH group here on the middle carbon, right? The other possibility that you have is the OH is on the end carbon like this. Okay, and here, since they haven't specified, you can show it like this. You can show it as a displayed formula, you can show it as a skeletal formula, however you want to represent it. Structural, skeletal, displayed, they're all acceptable, since they haven't explicitly asked for one specific type of structure. Okay, so again, the possibilities that you have is, the way to solve this type of a question is, they've given you a straight chain. Okay, the way to solve this type of a question is, first figure out for a straight chain how many possibilities are there. For a straight chain, there's 2 possibilities. There's butane 1-ol or butane 2-ol, which they've already given, right? Again, this would be position 2 and this would be position 1. So position 1 and position 2 are the only 2 possibilities with a straight chain. So butane 1-ol. And then with a branched chain, there's either methylpropane 1-ol or you have methylpropane 2-ol. Okay, the OH and the methyl group are on the same carbon, or the OH is on carbon number 1 and the methyl is obviously on carbon number 2. Okay, so these are your 2 possibilities, or 3 possibilities. Okay, 2 reactions of X are shown. In the first reaction, the secondary alcohol is being converted into a ketone. In the second reaction, the secondary alcohol is being converted into an alkene, C4H8. What's the type of reaction in reaction 1? when a secondary alcohol is converted into a ketone. That is the oxidation of secondary alcohols, right? It's a redox reaction, but obviously the oxidizing agent undergoes reduction. As far as the secondary alcohol itself is concerned, it's being oxidized to form a ketone, okay? And the reagents and conditions that we can use is you can use acidified dichromate or you can use acidified manganate. So we use acidified dichromate. So these are the reagents you need, okay? You can also use acidified manganate, as I mentioned before, okay? And the observation here would be the solution, the dichromate would go from orange to green, okay? Reaction 2 can be carried out by passing the vapor of X over hot aluminum oxide. The product of reaction 2 C4H8 is actually a mixture of three isomers. Give the full names of the three isomers formed by reaction 2. So they're saying that if I take this guy over here, and I react it with aluminum oxide, I react this with aluminum oxide, I produce three different products. Okay? I'm using Al2O3. This is elimination of H2O, right? It's a dehydration reaction to form an alkene. Now, this because they've given us the molecular formula, we have C4H8, right? Now, what are the three different products I can have? I can either remove the OH and the neighboring carbon's hydrogen to form but-1-ene. Okay, I can form but-1-ene over here. I can form but-1-ene. Now, what about the other possibility? If I remove the hydrogen from here instead of here, right? If I make the double bond here, I remove the OH and the H. Okay, I remove the OH and the H over here, right? Then I produce but-1-ene. If I remove the OH here and the H from the middle carbon, I produce but-2-ene. But but-2-ene is what? But-2-ene is this, right? CH3, CH double bond, CH, CH3. Does but-2-ene actually exist as a single isomer, or is it two different things? This structural formula, does it represent just one species or two different things? But-2-ene over here can be cis but-2-ene or trans but-2-ene, right? But-2-ene can be cis but-2-ene or trans but-2-ene, right? You can either have this alkene being produced, right? This is the cis isomer, or you can produce the trans isomer, right? So there are two possibilities for but-2-ene. It's either cis but-2-ene or trans but-2-ene, okay? So it's actually but-2-ene is not a single substance. It's either cis but-2-ene or trans but-2-ene. So the three isomers that are produced over here are, you have but-1-ene, okay? You have but-1-ene. Then you have cis but-2-ene, and you have trans but-2-ene, okay? Again, over here, they both have the same structural formula. They both are CH3, CH double bond, CH, CH3. Okay, but this structural formula actually represents two different things. This can be the cis isomer or the trans isomer. So but-2-ene is actually not a pure substance. It's either cis but-2-ene or trans but-2-ene. They're two different alkenes. Okay, they're stereoisomers of each other. So they both have the same structural formula, but in three dimensions they look different. Okay, the cis isomer and the trans isomer. The reaction of methyl propene with hydrogen bromide produces a mixture of two halogenoalkanes. One of the halogenoalkanes, 2-bromo-2-methylpropane, is formed as a major product, while 1-bromo-2-methylpropane is formed in small quantities. Complete the mechanism to show the reaction of methyl propene with HBr to form the major product. Include the structure of the intermediate and all necessary charges, dipoles, lone pairs, and curly arrows. The structure of 2-bromo-2-methylpropane is not required. Alright. So what we have over here is this is electrophilic addition, right? We have a delta plus and a delta minus. The electrons from the pi bond go to the hydrogen, and the HBr bond, right, undergoes heterolysis. And what you end up making is a carbocation intermediate. Now my question is this. If you look at the carbon atoms here, over here, which carbon atom will the hydrogen go on? Will it go on this carbon or this carbon? Will it go on the one on the left or the right? Where will the hydrogen go? Because we're going to get a carbocation, right? The hydrogen will go on the carbon with more hydrogens so that we produce this carbocation, right? The hydrogen will go here so that we produce this carbocation. This is a tertiary carbocation. The carbon with the positive charge is bonded to three different carbon atoms. Okay. If the hydrogen went here and the positive charge went to the right, then we'd have a primary carbocation, which is not as stable. It requires more activation to form. Okay. So here we're going to form this tertiary carbocation, and then in the second step, the bromide, okay, will go and attack this carbon and bond to it to form the final product. So you're going to have a bromine atom over here. Okay, that's the major product. Okay, so why is 2-bromo 2-methylpropane the major product? It is because it is formed via a tertiary carbocation intermediate. It's formed via a tertiary carbocation intermediate, which is more stable than the primary carbocation intermediate due to the positive inductive effect of the alkyl groups. Okay, due to the positive inductive effect, or you can say due to the electron donating effect of the alkyl groups. Positive inductive effect, okay, of the alkyl groups. All right, this positive inductive effect is also the electron donating effect. But positive induction is the proper term for this.